Steve, for the invitation, and it's convenient to speak on Zoom, but it's also nice to be able to be there in person. But given the circumstances, let's see. Okay, so let's see if I can. Sorry. So this the KPZ equation models the growth of a generic randomly growing surface, and it's been a sort of hot topic in probability for a while, and lots of people working on it. So this is the equation. I'm sure you have seen it before, but in any case, let me show you. So let's say ftx is the height of a d-dimensional surface, random surface at time t, non-negative real number, and location x, which is an r to the d. The KP's equation says that it evolves as follows. You have the time derivative of f is some constant nu times the Laplacian of f plus some lambda over 2. So this is how the phase is written, So you could as well put lambda, but anyway, let me write it in this way: lambda over 2, the gradient f squared, plus square root of d. D is another constant times psi, where psi is a random field known as space-time white noise. And formally, this random field is a centered Gaussian random field, and it's a distribution valued field whose covariance is given by this. So if you imagine that you can take the covariance between the field at 2 points tx and t prime x prime, it's the Dirac delta t minus t prime and Dirac delta in Rd of x minus x prime. So it's basically a bunch of, you can think of it as like independent random variables, one at every point in space, but with infinite variance, and things are adjusted so that if you take the integral of this random distribution on some region, you will get a normal random variable with mean zero and variance equal to the volume of that region. Okay, so that's space-time white noise, and this can be rigorously defined. There is a big literature on that. So, so this can be defined rigorously, the space-time white noise, but the rigorous definition of the KPZ, of a solution of the KPZ equation is a difficult problem. And the main difficulty is that you see this gradient squared here. So if f is a distribution, then its gradient is also a distribution. And if you want to take the square of it, you have to multiply distributions. And there are many well-known difficulties in defining products of distributions. This is one thing that leads to a lot of trouble. So now in dimension 1, this has a complete solution. And there are many techniques, most prominently, there's this revolutionary technique of Martin Heirer of regularity structures, but even before that, there was a Kohlhoff solution. And then after that, you have paracontrol distributions. There are also notions of energy solutions, and there is work on the mathematical physics side using renormalization group. So there are, we now have a more or less clear understanding what this equation means in dimension 1. Okay? And moreover, many one-dimensional discrete processes have been shown to have a KPZ scaling limit. So you take some scaling of space and time, and you look at the limit of these processes, and in an appropriate sense, they converge to one of these solutions that have been defined here. And lots of people have worked on that, and there are several excellent surveys that are available, which you can look, and the literature is growing every day. So I can't discuss all of that here. So in dimensions 2 and higher, the situation is much less satisfactory from the mathematical side. In particular, dimension 2 is the most important dimension because surface is typically two-dimensional, right? So that's the physically important case, and also for other reasons. And there are some recent construction of distribution valued solutions. So the one-dimensional solutions are all function valued. They're very rough functions, sort of like Brownian motion, but they're function valued. And there, you don't know what is the gradient because these functions are not smooth. So that's one of the things that prevents us from rigorously defining the solution of the KPZ equation in some easy way. But it can all be made sense of. But in 2 dimensions, the only constructions that exist right now, 2 and higher dimensions, are distribution valued solutions. And I have been involved in that in one of the papers, and there are other people. Unfortunately, the solutions are what physicists would call trivial. I mean, mathematicians would say trivial, a function is trivial if, if it's zero everywhere or constant everywhere or infinite. Physicists would say trivial if the solution is Gaussian. Okay, so they say trivial somehow means Gaussian, and non-trivial solution has not yet been constructed, and there are conjectures in physics. So I'll talk about that. So a fundamental roadblock to constructing non-trivial solutions to the KP's equation in dimensions 2 and higher is that we don't know how to take scaling limits of these approximate solutions to reach a non-trivial limit. So the solutions I talked about in the previous slide are obtained like that. You first have an approximate solution which is well defined, and then you take a limit in a certain way, and you reach a solution which is a random distribution, which turns out to be a Gaussian process, and it's actually a solution of a simpler equation known as a stochastic heat equation with additive noise, with some other parameters. So somehow this all leads to some kind of triviality. But the physicists tell us that there are ways to get non-trivial limits. So even in one dimension, there can be many different scaling limits, but in many one-dimensional models, we at least know one way of taking a scaling limit that leads to a non-trivial solution. In 2 and higher dimensions, the question becomes much less tractable. So for example, in 2D, the physicists believe that there is a certain kind of scaling known as this family-Vichak scaling. They believe that's the correct one and leads to a function valued rather than a distribution valued solution of the KP's equation, 2D KP's equation. Okay, and we don't even know what are the right exponents, how to take that scaling limit. And this has been verified in numerical simulations, but remains out of the reach of rigorous mathematics, or even theoretical physics arguments. It remains out of the reach of that. So the situation is very murky, as one might say. So this is the current scenario. Very, very briefly, what's going on in one-dimensional KPZ versus higher dimensions, and it would be I think okay to say that we don't really understand in 2 and higher dimensions, and the physicists tell us that in 3 and higher dimensions the whole situation becomes sort of much less interesting. So the main interesting thing is 2 dimensions. That's what I keep hearing. Okay, so in this talk, I will present a small step towards understanding KPZ in general dimensions without confronting this issue of constructing scaling limits. Okay, so what do I mean? So this is based on some framework that I introduced recently in some papers. Now, since this correct way to scale is still a mystery, I propose the following workaround. So consider a general class of growth models, which contains at least one class of one model of widespread interest. So it's not something that is completely made up. And then show that irrespective of how you take a scaling limit, the growth is always locally like the KP's equation, breaking up as a sum of a Laplacian term, a gradient squared term, a noise term, and a residual term that is negligible compared to the other 3 terms and their sum. So you just look at, you don't try to construct, the limit object, because we don't know what space it should be, how we should scale, etc. You just look at the local growth. You just look at the discrete process. What happens if you grow a little bit, and you try to show that little growth breaks up as a sum of exactly what the KP's equation says: a discrete Laplacian term, a discrete gradient squared term, and a discrete noise term, plus a residual term, which you then try to show that it's negligible compared to all the other terms and also their sum. So it's really like the KP's equation, but we should have this irrespective of how you take a scaling limit. Okay, so because we don't know how to take a scaling limit, so it should be, so this seems, either impossible or trivial, or so it's how you think about it. But surprisingly, this is doable, and as far as I can see, it's neither impossible nor not trivial. So I'll tell you the details in the following slides. You can actually do this. Okay, so this is actually possible to do this. Okay, so I've been thinking about it for a while, and so I'm very happy that I can present a solution to this. So let's first define this local KPZ growth. What is meant by local KPZ growth? So take any dimension D. Suppose you have a collection of discrete surfaces. So you have a collection of functions f epsilon from, time is now discretized, non-negative integers. Space is also discretized, z to the d. into R. So you have a collection of discrete random surfaces. Now I can define a general rescaling of f epsilon as follows. How do you take a scaling limit? So let alpha, beta, and gamma depend on epsilon, are positive real numbers, so that alpha and beta tend to 0 as epsilon goes to 0. And then you define f super epsilon tx. Now the arguments of f super epsilon are real numbers. This is non-negative real numbers. This is in R to the d. So you define just as gamma epsilon times f sub epsilon times alpha inverse t and beta inverse x. So these are the ceiling, taking the integer part. Okay. So this means that what we're doing is we're rescaling space and time so that successive time points are separated by alpha epsilon and successive neighboring space points are separated by beta epsilon. So this is very common in the KPZ literature and other literature on scaling limits. And gamma epsilon is just a multiplicative factor meant to ensure that the limit is not some, you don't shrink to 0 or blow up to infinity, you get some object. So I'll give you an example later on, how of a process that's actually done in this randy. I'm sure you have seen in talks on KPZ, that in dimension 1 you sometimes take alpha to be minus 2/3, 1/3, all those exponents. So so this factor gamma epsilon is just a multiplicative factor. Okay, so this is a general formulation of a scaling limit. So so you have these rescaled functions, and notice that I'm not talking about the convergence to anything. So I'm just saying that you have these discrete random surfaces, and you have these rescaled functions, this rescaled random surfaces, which you want to take a scaling limit of. Any questions until now? So, in Zoom talks, I just whiz by and can never see the faces, never understand whether people are following. So just, unmute and ask me if there is any question, and interrupt me anytime you want, even if I'm speaking. Okay.
Excuse me, I don't really understand that a gamma epsilon. So that will converge to 0 or explode to infinity, or
no? That is completely arbitrary. So it can converge to 0. It can explode to infinity. It's just a multiplicative factor. When you're taking a scaling limit, it's a multiplicative factor meant to ensure that this whole thing converges to a non-trivial limit. Okay. So there is
and you want to choose some gamma epsilon to.
Yeah, you want to choose some gamma epsilon. So there is no restriction on gamma epsilon. I just want alpha and beta to go to 0 because these are the successive time and space points. You want their separation to go to 0. Okay.
Okay. Thank you.
Okay. So so the step 2 is let A be the set of the consisting of the origin and its nearest neighbors in the lattice ZD. So this A will be fixed throughout this talk. Define the local average of this rescaled function as the following. So you take any tx and you look at all its nearest neighbors and itself and take the full average of that. So there's a local average of f in this small neighborhood. Okay. Beta epsilon, remember, was the separation of space points. So this is just looking at the rescale lattice and looking at the neighborhood of tx in that rescale lattice and taking the average value. So then you define the approximate time derivative of f epsilon as the following: discrete time derivative. So you take one small step in the time direction, take the difference of the function, divide by alpha epsilon, define the approximate Laplacian as you take the local average of f around that point minus the value of at f at that point divided by beta epsilon squared times some suitable factor 2d plus 1. Then you define the approximate squared gradient as this. You take the f epsilon at all the neighboring points minus the average value squared, and then and these definitions are inspired by the fact that if alpha and beta are going to 0, then f epsilon converges in some strong sense, some smooth function. Let's say, just for fun, let's say it's converging to some smooth function in some strong sense. Then the approximate time derivative, the approximate Laplacian, the approximate squared gradient all converge to the corresponding things for the limit. So the actual time derivative, the actual Laplacian, actual gradient square. So this is how these are defined. So these are these approximate things, but of course we do not expect in general these f epsilon to converge to some smooth limit, but these are mimicking these limiting things as if you're converging to a smooth limit.
Excuse me, could you go back 2 slides? I forgot some notations.
Yeah.
Just to take one more.
Sure.
One more. Go back one more. Yeah. Okay. Thank you.
Okay. So this is the rescaled function, rescaled version of f sub epsilon. And then with this rescaled version, you define these approximate time derivative Laplacian and gradient squared. And then with these definitions are inspired by this, that if f epsilon was converging to a smooth function, then they would converge to the corresponding things. And then we do not expect that, but we can still define it. Now, here's the definition of local KPZ growth. So we'll say that f super epsilon has local KPZ behavior as epsilon goes to 0, if for some strictly positive nu lambda and d, which can also depend on epsilon, and for some random maps, I don't know, somebody's waiting, okay. For some random maps, psi epsilon and r epsilon on the space, you have the following, that this approximate time derivative is nu epsilon times the approximate Laplacian plus lambda over 2 times the approximate squared gradient plus square root d times the approximate, this is the approximate white noise that we are constructing, and a remainder term. So this is an exact identity. So we'll have this exact identity such that this noise term is independent of the other terms, okay, for a fixed tx. Note that tx is now fixed. So this is independent of the other terms on the right side. This psi epsilon converges to white noise on this space as epsilon goes to 0. So I'll not tell you what that means, but you can understand that there is a notion of white noise as a random distribution, and this is converging to white noise in law. And this remainder R, that's the most important thing, is little OP of the first 3 terms and their sum, in the sense, which means the following, that if you take this remainder, so Tx is fixed, if you take this remainder, divide by any of these terms, they go to 0 in probability as epsilon tends to 0. And also if you divide by their sum, that also tends to 0 in probability as epsilon goes to 0. So it's really small compared to this right side. So these 3 terms give you the leading order behavior, okay? So that's the definition of local KPZ behavior. So I'm not talking about taking any kind of, or constructing any kind of limit object. I'm just saying that you have some notion of a scaling limit. You scale space-time in a certain way, multiply by some factor. And then you say that these functions have local KPZ behavior if this holds, okay? If your growth breaks up into this Laplacian term, the gradient squared term, and the noise term, and the remainder term, which is negligible compared to the other 3 terms. Any questions? Okay, so it seems reasonable. So one remark is that it may seem as if this new lambda and d should not be allowed to vary with epsilon because the coefficients in the KPZ equation are constants. But this is not true. In the KPZ literature, it's understood the coefficients can be allowed to vary when taking the scaling limiter, and even be allowed to tend to 0 or blow up to infinity. So the representation that you see in terms of nu lambda and d, it's just a formal representation. Okay, and this is especially true in dimensions higher than 1. For example, this family Dirichlet scaling, this requires this. This actually needs these coefficients to vary with as you take the scaling limit. And the important thing is that we want time derivative to decompose into a linear combination of the Laplacian, the squared gradient, and independent error with a negligible error, and that's independent noise with a negligible error. So this is captured by this definition. Okay. So let me now give you a theorem. Okay. So I'll define a general class of growing surfaces which contains at least one model of interest, and show that you can have this local KPZ behavior under any scaling limit. Okay, so recall that A is 0 and its neighbors. Let phi be a function on R to the A. Let Z be a collection of IID random variables which index by time and space, which we'll refer to as a noise field. Now, given a epsilon bigger than 0, define a function f epsilon as follows. At time 0, it's identically 0. So you start from an all 0 initial condition. Then at time t plus 1, it's defined as phi of f epsilon t x plus a over all a in a plus this epsilon times the noise. So this, if ftx is a function, is the height of the d-dimensional random surface at time t and location x, this recursion says that at time t plus 1, the height is a function of the heights at x and its neighbors plus an independent random fluctuation. Okay, so it's completely, general setup, except that you have the synchronous increases, so at all locations. So you can have in probability, we have many models in probability and physics where increments happen at Poisson intervals of time independently at each location. So this is not captured by that. So this is a class of models where every height, every location, the height is updated at the same time. Okay. So you have ft plus 1x is this phi of ftx plus a in this a plus this epsilon zt plus 1x. So this is the setup that I introduced in an earlier paper this year, but without the noise. So I introduced the noise in this paper, and so we later see that this model of directed polymers in random environment can be put in this framework. Okay, so there is at least, this satisfies this condition. There is at least one model of interest which is in this framework. So now I make some assumptions about phi. So until now, this is completely general. You have a phi function phi. Now I put some assumptions. So let's see some notation. 1 denotes a vector of all ones. If u is a vector, then u bar denotes the average of the coordinates. And if u and v are two vectors, we write u bigger than or equal to v if u dominates v in each coordinate. Simple notations. So we make the following assumptions. We assume that it's equivariant on a constant shifts. So if u is a vector and c is a real number, if you add c to each coordinate of u and apply phi, you get phi u plus c. So that's a reasonable assumption. That is, if the whole surface is raised by a constant amount, then at the next step also, the new surface is also raised by the same constant amount. Then I assume it's 0 at the origin. This is not a restrictive assumption because, if it's not, then you can just subtract off phi 0 and define a new process, and the new process is related to the old process in a simple way. Then I assume monotonicity. So if one surface dominates another completely, then at time t, then at time t plus 1 also, then it will do so if you apply the same noise. So if u is bigger than or equal to v, then phi u is bigger than or equal to phi v. Then I assume symmetry, which means that you have that phi is a symmetric function of the coordinates. And then I assume some regularity. The phi is twice continuously differentiable in the neighborhood of the origin. So this is actually important because this in my paper at Tsuganidis, we show that if this is not true, and that's with no noise, then you can have things that are not really KPZ. Assume a non-degeneracy condition that the Hessian matrix of phi at the origin is non-zero. Okay, so again, you need this for KPZ. And so these are all sort of regularity things, and these things have appeared before in the literature on convergence of discrete approximations of partial differential equations, the equivariance and a constant shift, monotonicity, in particular, they are quite important in the literature. There's one more crucial assumption, and this is the main assumption, which I state in the next slide, which is the Edwards-Wilkinson domination, the strict Edwards-Wilkinson domination. So the Edwards-Wilkinson model is a model where phi is the average. So the Edwards-Wilkinson model is that you have a random surface. How it grows is the following: at each time, you take a point, look at the height at that point and its neighbors, take the average of those, and you add a random noise. Okay, so that's the Edwards-Wilkinson model. And that's a very simple surface growth model that was introduced actually before KPZ, before Carter, Parisi, and Zhang. And the motivation of the KPZ paper was that the Edwards-Wilkinson was not capturing the essence of many actual models that they were using. So it's an improvement of the Edwards-Wilkinson model. So the Edwards-Wilkinson model is where phi u is just the average. So we assume that our surface grows at least as fast as that, meaning that phi u is at least the average. So the function at time t plus 1, the growth is at least the average of the neighboring points plus some random error. And moreover, we assume that this domination is strict in the sense that if un is a sequence so that phi un minus un bar is going to 0, then un minus un bar times 1 also goes to 0. So in particular, you can have equality if and only if u equals U bar at each coordinate, and you cannot have that at infinity also. So this kind of captures that. So this is the main assumption, that you have this Edwards-Wilkinson domination condition. Any question about the assumptions?
I had one. This is Peter. The symmetry, there's a preferred point in A, which is the center point. I mean, I can understand how all the other directions want symmetry.
Yes, so I did it for simplicity, actually. So you can have that it's symmetric in just the other things, not the center point, but the theorem would get a bit more complicated with that, notationally. So I just assumed that, and I'm working with that. And for example, if you don't have the symmetry, then phi can just be a function of the neighbors, excluding the center. And then it will lead to parity issues, so then the whole setup has to be made a little more, notationally complicated. So I want to avoid that. So, but yeah.
So things can be done in that case, but it's just a little messier.
Yeah, it's messier.
Yeah. Okay, thank you.
Yeah. So this assumption is called strict Edwards-Wilkinson domination. Okay. Any other questions about the assumptions or anything? Okay. So we'll later see that the model of directed polynomial random environment satisfies all of the above assumptions. And we also make a small list of assumptions about the noise field. We assume it has mean 0, which is not really a restriction. This is very important. It's a bounded noise field. So for example, you don't have Gaussian variables. And it seems to be very important for the proof. I don't know if the proof will go through without this assumption. So I don't know. I mean, some version of the theorem is true without this. So there's some constant B, so that the noise variables are bounded by this, and we assume that the law of the noise variables is absolutely continuous with respect to the Lebesgue measure. Okay. So these are the three assumptions I make about the noise variables. Okay, so here's the main result. Let f epsilon be defined using phi and the noise field z, as in the preceding slides. Suppose that all the stated assumptions about phi and z are satisfied. Let alpha, beta, and gamma be positive real numbers depending on epsilon, and let f super epsilon be the rescaled version of f sub epsilon using these. So here is the theorem. For any choice of alpha, beta, and gamma, so that alpha goes to 0 and beta goes to 0, epsilon goes to 0, f epsilon's local KPZ behavior as epsilon tends to 0. Okay. So if the assumptions that I stated are satisfied and f epsilon grows like this, then you have local KPZ behavior no matter how you scale time and space. Okay. And so the explicit formulas for nu, lambda, and d can be given in terms of epsilon and this alpha, beta, and gamma and the Hessian matrix, but I'll skip that. So it's sort of a little messy, so I'll not state those. So this is the main result. Okay. Any questions?
Oh, sorry. The formulas for the parameters like lambda and d, depending on alpha, beta, and gamma, are these? Is there some kind of like regularity? Like, are they continuous in some topology based on?
Yeah. So that they're not hugely messy. It's just that I didn't want to state that. It's just they're rational functions. And so for example, nu may be beta squared over alpha, and lambda may be beta squared over alpha gamma times 2, something like that, and d is a little more complicated, but it's just all like alpha to the something, beta to the something, epsilon to the something, gamma to the something, and then there is some factor, something involving the Hessian. That's the kind of thing that you have.
Okay, yeah. just to understand the what you sort of want to say when you say a scaling limit is KPZ behavior probably is like you take the scaling limit and all these things are sort of non-trivial in the limit. All the constants, the lambda and the d and the nu are sort of all non-trivial in the limit. Maybe that's some kind of weak asymmetry scaling.
Well, yeah. Well, I see. The thing is, I don't know what is meant by these non-triviality. So all I'm saying here is this in this definition.
No. I understand. It seems like your result is quite cool. I'm just trying to ask if you have. Is there something you can do where you say, okay, if I have one scaling where if I have a scaling where each parameter is 0 and a scaling where each parameter is infinite, then there's going to be something in the middle where like all of them are non-trivial.
So I'll give you one example. So yeah, that's a good point. So for example, if dimension is 1, and suppose you want this new lambda and d to be all constants, not depending on epsilon. Let's say you want to ensure that. So then it drops out from the equation, from the formulas, that gamma should be 1, beta should be epsilon squared, and alpha should be epsilon to the 4th. And that's the intermediate disorder regime that Alberts, Cunningham, and Quastel they got for the polymers. So I'll mention that. So you have in dimension 1, it's always that. So if you want the coefficients to be constants, then you can choose this alpha, beta, and gamma. You have to choose them to be epsilon to the 4th, epsilon squared, and 1. So that's one thing. But in greater generality, I don't know, what.
Okay, great. Just want to check like to what degree you could like say, oh, there's some point where they're all non-trivial if we just know like each of them is non-trivial somewhere or something.
Yeah. So what I have in the, yeah, maybe I should add that too. So what I have in the theorem, if what I have in the proof, but I can state that as part of the theorem also, is that these 3 terms that you get, this Laplacian term, the gradient squared term, and the error term, or at least the Laplacian and the error term, maybe not the gradient squared term, they're of comparable size, together with the alpha and together with the nu and d, if you put them in, they're of comparable size, and the gradient squared term may be smaller. But yeah, so I don't really know about the scaling limits and how they would behave. And the thing is, the problem is that if you want to really understand global scaling limits, then you would want to know how things interact at various points, the correlations and all that. And this theorem says nothing about that. It says just that at one point you have the growth breaks up as like that. So it's going from local to global is challenging. So I'll talk about that later.
Great, thank you.
Okay, so let me just make a remark. So it's not hard to guess that the local KPZ behavior must be some kind of consequence of Taylor expansion. But the main problem is that to invoke Taylor expansion, we need that for neighboring points x and y, the heights are close. F epsilon tx is close to F epsilon ty. So now I'm looking at the unrescaled function on the lattice. Okay. So this is trivially true if t is 0, because the functions is all 0 at time 0. So using induction on t, one can deduce that this continues to hold as long as t does not exceed some threshold determined by epsilon, when epsilon is very small. And maybe you can try to improve this and so on. But for the theorem to be true, we need that f at 2 neighboring points is close and continues to be close, even if t is allowed to vary arbitrarily as epsilon goes to 0. So that's the main challenge. So the nature of the surface is such that f at 2 neighboring points are close, the values of f, if epsilon is small, even if the t is blowing up very fast as epsilon is going to 0. In particular, t can blow up to infinity in any way it likes as epsilon goes to 0, and you still want this. Okay, so I'll give you a complete sketch of the proof later. I hope I'll have time. And although it's not very long, it's not clear why it works, and it would be important to have a more transparent argument, because as I just said, that to go to global, you need much more information. If you want to have global, KPZ behavior rather than local, you want much more information, and this proof is not giving that, and it's not clear how it's working. So anyway, I'll give you the sketch. So here's the example. So recall again, A is a set of the origin and its the set of its neighbors. Now you take a specific phi. You define phi u to be log of 1 over 2d plus 1 summation e to the ua. Okay, so you take e to each coordinate, take the average, and take log. So it's easy to check that it's equivalent in a constant shift. So if you add a constant to u to each coordinate, the whole thing just shifts by a constant. It's 0 at the origin. That's easy to check. Monotone, symmetric, obviously, twice continuously differentiable, and the Hessian function at 0 is non-zero. Okay. Okay, and also the Hessian is positive semi-definite everywhere. That's also easy to check, which shows that this function is convex. And the following lemma shows that phi has a strict Edwards-Wilkinson domination. So here's the lemma. So you have a function which satisfies all the other conditions except the strict Edwards-Wilkinson domination, and you know that it's convex. Then it also satisfies the Edwards-Wilkinson domination condition. Okay? So this lemma will tell you that this function satisfies all necessary conditions. And this function is what gives rise to this directed polymers in a random environment. Let f epsilon be the discrete random surface generated using phi in the previous slide and a random field. And by induction, it's easy to show the following, that f epsilon tx is log of 1 over 2d plus 1 to the t minus 1, sum over all p in the script pt. I'll tell you what these are. E to the epsilon times this sum, where pt is a set of all p0, p1, pt minus 1 is e to the d, so that you start at 0 and the successive points are separated by distance at most 1, where this is the Euclidean norm. And this log partition function of the d plus 1 dimensional directed polymer model on lazy random walk paths starting of length t minus 1. So typically, this directed polymer model consider random walk paths, but I'm taking this lazy random walk path again just to avoid notational mess because of these parity things. So, but the essential features of the model should all be the same, whether you consider random walk paths or lazy random walk paths. So this is the log partition function, and this is the surface that's generated by the directed polymer model. And by the main result that I displayed 2 slides ago, f epsilon has local KPZ behavior under any scaling limit if these are continuous bound, the random variables in the environment are continuous bounded and have mean 0. Okay. So this is the example. And so I'll tell you what is known about this model in the next couple of slides, but any questions before that? Okay. Okay, so what is known? Again, I'll not be able to cover everything, but one of the important results is a result of Alberts, Kanin, and Coastel from 2014, who showed that a non-trivial global KPZ limit can be obtained for the 1 plus 1 dimensional directed polymer. So D is 1. By taking in our language, in the language that I stated, they of course stated differently in different language, but what I stated now, you have to take alpha proportional to epsilon to the 4th, beta proportional to epsilon squared, and gamma proportional to 1. And they call this the intermediate disorder regime. So epsilon, remember, in our setting, epsilon is the inverse temperature, so which is going to 0. And they have this n to the minus 1/4 scaling for the intermediate disorder regime. So n is this 1 over alpha, that's n. That's the number of time points that you're going. So that's why alpha should be epsilon to the 4th. Now, the fact that I stated a few slides ago is that in our setup, if we want the coefficients to not depend on epsilon, and the dimension is 1, then we must take this scaling. So this matches above scaling, exactly. Okay. Now, even for dimension 1, this is not the only way to get a non-trivial scaling limit, but this is the only one to have been rigorously analyzed. The other possible limits have not been rigorously understood. When dimension is 2, then a physical trivial limit, as I stated, random distribution, is obtained by taking alpha to be proportional to e to the minus c epsilon to the minus 2 for some constant c, which has to be sufficiently large, actually. And beta like square root alpha, and gamma like epsilon inverse. And this limit is random distribution. And this, I did it in a paper with Alex Dunlop, and then it was improved in his papers. And in his two papers, it was shown that the limit is physically trivial, which is equivalent to Edwards-Wilkinson growth with some other parameters. And for dimensions 3 and higher, there have been similar results that were obtained. But the thing is, as I said, in dimensions 2 and higher, there is currently no mathematical understanding of non-trivial scaling limits of the directed polymer model. And there are conjectures, but there is no rigorous result. And of course, there are other things. I'm still trying to look at the literature. There have been a whole lot of things done in the last 2 years on KPZ in dimensions 2 and higher. So I may be missing something. Okay, so here's a sketch of the proof. So let me actually show you a proof. So you define the local average of f epsilon. So remember, f sub epsilon is the random surface on the discrete lattice. Okay, we're not taking scaling rescale things. So the local average here is just you take all the neighbors of x and you average them and you get this value. So suppose f has this thing that ftx is close to f epsilon tx plus a for every a. Then by using Taylor expansion, the properties of this function phi, the equivariance and the constant shifts, the and regularity near the origin and non-zero Hessian, you can show this. This is not hard to show that the increment f epsilon t plus 1 minus f epsilon tx breaks up as the sum of the Laplacian, discrete Laplacian, plus some constant times the discrete gradient squared, plus the random error, plus a remainder term of smaller order, which is not immediately obvious. The remainder term is actually of smaller order. The remainder term is smaller order than this, but how about this and this? So that's not clear. But let's say this is of smaller order. It breaks up like this using Taylor expansion. Now, so you have that. That's not hard. But the thing is, to get the local KPZ behavior under arbitrary scaling limits, as I said before, we need that this assumption here needs to hold even if t and x are allowed to vary arbitrarily as epsilon goes to 0. Okay, so how do you get that? That t this closeness of neighboring points holds even if t and x are allowed to vary arbitrarily as epsilon goes to 0. Okay, so step 1 is the following. So recall how f epsilon was defined. F started with 0, all 0 at time 0. At time t plus 1, it's phi of f epsilon at t x plus a over all a in the neighbors plus epsilon, this random part. Let del a phi denote the derivative of phi in coordinate a. By the equivariance under constant shifts, you have this identity. Now take derivative of in c at c equals 0, which gives you this, that the sum of the partial derivatives is always 1 at any point. If you take the partial derivatives and you sum them up, you always get 1. And by monodicity, these are all non-zero. Sorry, these are all non-negative. Okay. So if you are trying to follow the proof and lose track at some point, just stop and ask me. Okay. So at any u, the derivatives of phi are non-negative and sum to 1. So they give a probability measure. Okay. Now fix a realization of f epsilon and some points t and x, and define a random walk on ZD as follows. The walk starts at x at time t and goes backwards in time until reaching 0. If the walk is at y at time s, it goes to s minus 1 to a neighbor of y with probability equal to the partial derivatives at those points. Okay, so we just showed that the sum of the partial derivatives are all non-negative and sum to 1. So given a realization of f epsilon, you have all these, you have a legitimate random walk defined like this. So by the observation from the previous slide, these numbers are non-negative and sum to 1. This describes a random walk on ZD moving backwards in time, given f epsilon, given a realization. For each x and t, you can start a random walk at location x at time t and go backwards, where the probabilities of jumping to neighbors are determined by these derivatives. And inductively, one can show the following. So I'll not go through this. It's a simple induction. Inductively, one can show that, one can show that, so this is the important thing, that the derivative of f epsilon at time t and location x with respect to any ZSY, any noise variable, is epsilon times the probability that the random walk at time s is at y. Okay. So, so this gives you this exact formula. Okay. And the important thing is that these derivatives are all non-negative and sum to 1 if you sum over all y fixing s. So if you take all the noise at a certain time and you fix your tx and you have the value of your function at time t location x, and you take the derivative of that value with respect to the noise variables at some earlier time, every noise variable, and you take this derivative. These derivatives are all non-negative, and they all sum to, well, not one, but sum to epsilon, because it's a probability. Okay, so so this is a more general thing. You can have the noise entering in nonlinear way also, and you can have a similar representation. And there is also an easier way to see this, which is that you can inductively prove that if you look at the noise variables at any time, and you look at the value of the function at a specific time and location after that time, the function, that value as a function of all the noise variables at a specific time is again equivariant under constant shifts and monotone, and which gives you again that the derivatives should all be non-negative and should sum to 1. So in particular, you have this, that if you take any tx and you look at any fixed s less than t, and look at the derivative of f epsilon with respect to z s y, these are all non-negative. So if you put absolute values that don't change and you sum them up, you just get epsilon. Okay. And what this implies is that by this identity and the multivariate mean value theorem, you can show that if z1y, the noise at time 1, is replaced by 0 for every y, so every noise variable at time 1 is replaced by 0, then the value of the function at time t and tx changes by at most b times epsilon, where b is the constant upper bound in the magnitude of the noise variables. Okay, so you have the noise variables are bounded. So this is where I need noise variables are bounded. So you have the noise variables are bounded. You replace everything at time 1 by 0. The value at a point, value of the function at a point changes by at most b times epsilon. Okay, any questions about that? Okay, so let us do that. Let us replace all the noise variables at time 1 by 0, and you get a new value of the function. Let's call it g epsilon tx. So note that g epsilon 1x is 0 for all x. So this is how we set up the whole thing, because if you replace all the noise variables at time 1 by 0, you just get that g epsilon doesn't grow at all at time 1. And so g epsilon is just like f epsilon, except that we instead of starting with an all 0 initial condition, we now start with an all 0 initial condition at time 1. Okay, so it's like starting f, but with a delay. You start at time 1. So this implies that g epsilon t plus 1 comma x has the same law as f epsilon x t comma x. Okay, and this gives the following identity, that the expected difference between the heights at time t and t plus 1 at the same location equals expected value of f epsilon t plus 1x minus g epsilon t plus 1x. This is by linearity of expectation. You can first separate out the two things, and then you can use this fact. And so, for example, if you have the expected value of the square, you cannot apply this trick anymore. Okay, so that's one big problem, that I can only do it for the first order bound by this logic. Okay, and this is a coupling argument. If you think about it, it's a coupling argument. So you have this, and we know that this difference is bounded by b epsilon. So you get this general bound that the expected difference between the heights at time t plus 1 and t is always bounded by b epsilon, irrespective of the time, any time. Okay. So then the next step is to observe that the law of f epsilon tx is the same for all x, because it's by symmetry. You're starting from an all 0 initial condition. That's why. So this gives that the expected value of the local average at time tx is the same as the expected value of the height at that point at time tx. So the expectation doesn't change. Again, I use the linearity of the expectations. Again, this step also wouldn't hold if you have square and so on. So you get this, and you get this is bounded by b epsilon. So the expected value of the difference between the height at time t plus 1 and location x minus the average of the heights at time t and location, all neighbors of x is bounded by b epsilon. Okay. Any questions about this? Okay. So now the noise variables have mean 0, which means that the expected value of f epsilon t plus 1x is the expected value of phi of f epsilon t x plus a over all a in a plus this noise, and this has expectation 0, so you just get this. So you combine these two, you plug this into this, and you get that expected value of phi of q epsilon tx is less than b epsilon, where q epsilon tx is this vector. It's the vector of the values of f epsilon at x and all its neighbors at time t minus the average of these values. So that's a vector. And if you apply phi to that vector and you take expectation, that expectation is bounded by b epsilon. Okay. Okay, so how do you use this? So note that q epsilon belongs to this hyperplane of all vectors whose mean is 0, because q epsilon is just a vector minus its mean value. So q epsilon belongs to this hyperplane. Now, by Edwards-Wilkinson domination, phi is non-negative everywhere on this hyperplane. So phi, remember, phi u is bigger than u bar. So phi is non-negative everywhere on this hyperplane. So you can apply Markov's inequality to get that probability that phi of q epsilon bigger than eta is bounded by expected value of phi at q epsilon divided by eta. And we know that the expected value is bounded by b epsilon. So it's bounded by b epsilon over eta. So that's just by Edwards-Wilkinson domination. On the other hand, by strict Edwards-Wilkinson domination, we know that phi un goes to 0 implies that un goes to 0 on this hyperplane. Okay. So that was actually, it's a restatement of Edwards-Wilkinson domination. If you have a sequence un on this hyperplane such that phi un goes to 0, then un also goes to 0. Which shows that for any delta, there exists eta, so that if u is in h and phi u is less than eta, then u must be less than delta. The norm of u must be less than delta. So it's just equivalent to this condition. So this means that the probability that the norm of q bigger than delta is bounded by the probability that phi of q is bigger than eta, which is bounded by beta epsilon over eta. And note that this bound on this side, if you fix delta, this has no dependence on t and x. It just depends on epsilon. So q epsilon, remember, it's the vector of f epsilon at tx and its neighbor, f epsilon time t and all the locations neighboring to x minus its mean. So this shows that, if epsilon goes to 0 and t epsilon and x epsilon vary arbitrarily with epsilon, this shows that you still have that q epsilon, t epsilon, x epsilon is going to 0 in probability. This bound shows that. Okay. So recall that q epsilon is this, which means that we can apply Taylor expansion. So it shows that f epsilon, the value of f epsilon at x and its neighbors at time t is close to the average value, which means that all the values are close to each other. Okay. So this validates the Taylor expansion, and then there is more work needed to establish the remainder term is negligible compared to the other terms. So that involves some more work. This is the part that requires that the Hessian is non-zero, and I'll not talk about that. So the main open question, as I mentioned before, is that so this shows that KPZ behavior seems to be locally true for arbitrary scaling limits of the class of models under consideration, in particular for directed polymers. Now, can we expect something analogous for global KPZ behavior? And this does not seem totally unbelievable, but one has to formulate what is meant by global KPZ behavior in dimensions 2 and higher, which is, nobody knows yet what that really means. And so with this challenging question, let me thank you all and conclude my talk. Thank you.
All right, thanks very much. I'll encourage everybody to clap and say thanks, and I'll stop the recording.